All right, well, this is Mrs. Lee coming at you with stoichiometry of compounds, which is really just a very fancy technical way of saying we're going to do conversions. Conversions between grams and moles and grams. You've already done that. You've done using the molar mass from the periodic table. But did you also know that we can do stoichiometry, conversions that is, between moles and particles and moles? Well, what are particles? Particles are any, if you see the word molecules, or if you see atoms, or if you see formula units. Formula units is just the name that we give to an individual particle of an ionic compound. Right, so any of those three examples are all examples of particles. So particles is a generic term. If you wanted to convert between moles and particles, you would need to use the conversion fraction of 1 mole is equal to 6.02 times 10 to the 23 particles. But there's another stoichiometric conversion problem that we can do, and that's between moles and liters of a gas. If that gas is at standard temperature and pressure conditions, remember standard temperature is 273 Kelvin and standard pressure is 1 atmosphere or 101.3 kilopascals. 1 mole of any gas, doesn't matter what it is, as long as it is at standard temperature and pressure, will have a volume of 22.4 liters. Okay, so this is just sort of a graphic organizer helping us to keep track of the different kinds of conversion problems that you may be asked to do. All right, so we're going to work through a couple of these new problems that you haven't yet worked on, specifically with the volume. All right, so the first problem says how many moles are in 44.8 liters of helium gas at STP conditions? Okay, so the fact that it says STP conditions just tells you that you can go ahead and use the conversion fraction of 1 mole of any gas is going to have the volume of 22.4 liters. Okay, so what we need to do is to start with the number that is given to us, the 44.8 liters, and we need to set up a conversion fraction where we're going to put liters in the denominator and moles in the numerator. You know that in these conversion fractions you always write 1 mole and then you ask yourself, well, 1 mole is equal to how many liters? 22.4. Right, so if you do the math, liters will cancel. 44.8 divided by 22.4 is of course 2 moles, but we need to maintain our 3 sig figs, so we're going to have 2.00 moles is our answer here. Let's take a look at the second question. How many liters will 4 moles of oxygen gas occupy at STP conditions? Okay, so we're going to start with the given quantity of 4.0 moles. We're being asked to find out how many liters that is. So we set up a conversion fraction. We're going to put moles in the denominator so it will cancel. Liters in the numerator. 1 mole of any gas at STP conditions will have a volume of 22.4 liters. Moles will cancel, and so here we just have to do the math. 4 moles times 22.4 is going to give us 89.6 liters, but we want to maintain 2 significant figures, so that's going to round to 90 liters. Let's take a look at this third problem. How many molecules of O2 are in 8 grams of water vapor at STP conditions? Okay, so here what we see is we are given 8 grams, we're given mass, and we're asked how many molecules. That is, molecules are your particles. So it says STP, so if this is a gas, we're dealing with the 22.4. But let's see what this problem brings about. I'm going to go back to our diagram. So I'm going to go back a few slides here. Okay. In this problem, we are given grams. That means we are starting here. And we are being asked to find out how many particles that is. That's here. Okay, so in order to get to particles, there's not a road that connects these. So we can't go directly from grams to particles. Instead, we have to first convert it to moles using molar mass, and then we have to convert it to particles using Avogadro's number, that's 6.02 times 10 to the 23. What we won't need to do for this problem, we will not need to use the 22.4 for this particular problem because we're not being asked to convert it into liters. So let's go back to that problem. All right, we're starting with 8.0 grams. We're setting up a conversion fraction, grams in the denominator. We're going to have to convert it to moles first. So this is 1 mole of water, H2O, has a molar mass of 18.0 grams. Okay. If we stop the problem here and cancel grams, we will be left with moles. But we don't want our final answer to be in moles, we want our final answer to be in molecules. So we have to do one more conversion fraction where we will put moles in the denominator and molecules in the numerator. 1 mole of any substance will have 6.02 times 10 to the 23 molecules. So let's take a look. Our math here, the moles will cancel. And now the math becomes 8.0 times 6.02 times 10 to the 23rd. Take that answer and divide it by 18. You will get a number like 2.67555 something. We're going to round that to 2 sig figs, but it's 2.7 times 10 to the 23rd molecules. You should convince yourself that you can get that same answer on your calculator. Okay. Number 4. If you have 3.01 molecules of xenon gas at STP conditions, how much volume will it occupy? Okay, so now what we have is we're trying to figure out the volume from the number of molecules. Okay, I'm going to go back to that diagram, erase all my writing that I have on here from before. Okay. Now we have a problem where we are starting in particles. We are given the number of particles, and we are being asked to find liters. So what we need to do here is to first convert particles to moles, and then we'll use a second conversion fraction to convert moles to liters. Right? So for this particular problem, we will not need to consult the periodic table. We will not need to figure out the molar mass for this substance. So let's go back to our problem right here. We're going to start with the quantity given, 3.01 times 10 to the 23 molecules. We're going to set up a conversion fraction where molecules goes in the denominator and moles goes in the numerator. 1 mole of any substance is 6.02 times 10 to the 23. If we leave the problem here, molecules will cancel and leave us with our answer in moles. But we want to find volume. So one more fraction. Moles will go in the denominator, so it'll cancel. Volume in liters on top. We know that 1 mole of any gas at STP conditions, which this gas is, will have a volume of 22.4 liters. We can see here that moles will cancel, and the math becomes 3.01 times 10 to the 23 times 22.4. Take that answer and divide by 6.02 times 10 to the 23. When we get this answer, we'll round to 3 significant figures, and we'll get an answer of 11.2 liters. All right, throwback. Okay, throwback to an earlier unit. What if we have that sample of xenon gas from problem number 4, but if it's at non-STP conditions of 0.5 atmospheres and 546 Kelvin, what will the volume then be? Okay. When you have, and this is just sort of an extra something above and beyond the Rosengarten unit, but this would require the use of the ideal gas law, where you'd be solving for volume, which means you'd be dividing both sides by the pressure. So the volume of this gas would have some number of moles, which we're going to have to figure out here. R is the universal gas constant, T is this temperature here, and 0.5 atmospheres is that pressure here. So to solve for volume, we need to figure out how many moles of this substance we're talking about. So in this particular substance, we have, back in problem number 4, you had 3.01 times 10 to the 23 molecules, which, if you think about it, 3.01 times 10 to the 23 is half of 6.02 times 10 to the 23. So your number of moles in this particular problem is 0.500 moles. So plugging this number into this gas law equation, you get 0.500 moles times the universal gas constant of 0.0821 atmospheres liters over moles Kelvin times the temperature of 546 Kelvin. All that divided by the pressure given to us at 0.5 atmospheres. Okay, so when we do this, taking a look at atmospheres will cancel, moles will cancel, Kelvin cancels, leaving us with liters. Your calculator is going to spit this out at something close to 44.8 liters. If we are abiding by significant figure rules, this is our limitation right here. So this really would round to 40 liters. But the idea of the problem being the use of the ideal gas law to figure that one out. So, all right, there you have it. Compound stoichiometry and a little extra twist with the ideal gas law. I'll see you in the classroom.